So today, I know you guys saw it a little bit yesterday with Schwann's notebook, but you weren't formally introduced. So today we're going to do an introduction on machine learning. And so if you have questions, definitely feel free to stop me, and we're gonna, go through it step by step as much as we can. All right, so the first thing I want us to clarify, because I know some people know what machine learning is, some people are not as familiar, what is machine learning? And this is a question that I'm actually asking you, so I want an answer from the audience. What is machine learning? And perhaps, okay, perfect, Laura. Statistics, all right. Are you just answering that because your advisor is in the audience and that's what he would say? All right, how about someone else? What do you guys think? Yeah?
Combination of tools from econometric statistics to classify data or better understand data.
Okay, classify data, better understand data, all right. How about someone?
Or to solve some goals.
Okay. Okay. So, and the goals, goals is kind of vague. How would you define goals?
Tasks with data.
Okay, tasks with data. I like that. Anybody else have any other ideas? Yue, Jeeling, George, what do you guys think? No? No? No ideas? All right. Well, I think both Laura and Mihai covered it. So machine learning is a study of methods that use data to inform machines on how to solve a task. So there's always a task that you're trying to do, and there are different components that you need to optimize to solve said task, but this is, I guess, my best stab at how I would define machine learning. And this is helpful when you think about all the different problems that you're gonna wanna tackle with your own data in neuroscience, like what is your task? Are you trying to classify something? Are you trying to cluster something? Are you trying to regress something out? It's always important to come back to what does your data enable and what is the task that you're actually trying to solve with it. All right, and of course the method of choice, so what model are you going to use depends on the downstream class that you care about. And as an aside, we're not gonna really go into deep learning too much. We'll save that for next week. But deep learning is when the model you use to solve your task is a deep neural network. And so a lot of things that we've done so far has been machine learning, although people might not consider it. So PCA, machine learning. Using a deep neural network, also machine learning. So there's a wide range of the types of models that you can use, like linear all the way to nonlinear, and it's all just how do you learn from data to solve some task. Okay. So now we're going to go through some examples of tasks just so that you guys have a better understanding of how we can kind of put this in examples. So a first one, which is very classical, and I think a lot of people will probably want to do this with their own data, is classification. So if I give you an image, or if I give you two images, is the image on the left an apple or an orange? Very straightforward task. This is a kind of classic example of supervised learning. I have an image, I have a label. Can I, from the data, tell you what the label is? The second is clustering, which Lior is going to get more into tomorrow, I believe. And the idea is what signals in my data set are similar or different from one another. So you don't necessarily have labels when you're doing this, but you're using the data itself to figure out where do data cluster with one another, do they cluster at all? And then another example is regression. So, I'm just putting up an example here, but what function describes the relationship between a house's price and square footage? And so you can draw a line between these two factors and you can see, is there a relationship? These are not all of the tasks that you can do. There are many more tasks that you can solve with machine learning, but these are some classic examples just to prime your guys' brains with, what can we do? All right, so now what we're gonna look at is some of the previous topics that you guys have actually addressed in this course, and I want you to think about what task were you actually solving, and then tell me, what did you do? So one of the first things we did was, can we predict mouse attack behavior from linear combinations of neuron values? So I think we did this on the first day in one of Adi's notebooks. So what were you guys actually doing when you did this? Was it classification? Was it clustering? Was it regression? And within those categories, what were you doing?
I do remember it was called linear regression.
Okay.
So I'm going to jump from that and say we're doing regression.
Okay. All right.
And logistic regression.
Okay. So linear regression, logistic regression. Does anybody else have a different guess? No? All right, well, you both covered it. You were doing linear and logistic regression. We had two separate problems, and you were doing each of that. Another thing you guys did was, can you use principal components analysis to learn a simple yet rich representation of high-dimensional neural time series data? And what were you guys doing here? And someone else answer. It can't be Gregorios or Amit or Laura, someone that hasn't answered yet. I can go back if that helps. You already answered.
I think we did this lower dimensional space.
Okay.
Visualize the data, and through visualization, we realized there are kind of two clusters, a separate stacks or something.
Yeah, so we definitely did that. I think I classified this as unsupervised representation learning. So I kind of threw you guys a little bit of a curveball, but I just want you to always think when we're having you build a model, like what are you guys actually doing? What is actually the task? How does that fall into all the types of tasks that we can do? So, all right, so does this make sense how you're doing what we've done so far, how it fits into like some of the categories of types of learning in ML? Yeah.
What's the difference between representation and clustering?
Okay, so we're gonna get into what representation learning is in a few slides, and it's a very good question. Some people would say, we're gonna get into different types of learning, so let's maybe hold that for a few slides. All right. Okay, so examples of learning paradigms. So here, you guys have probably most been exposed to supervised learning, and this is when you wanna learn a function y equals f of x that predicts an output label from input data. So an example might be I have a picture of an apple and that's my input data and I want to be able to say, okay, that's an apple. So the label for the image is an apple. I want to take in the image and I want to be able to output, yes, that's an apple. All right, another type of learning is unsupervised. So this would be learning patterns from the data when you don't necessarily have the labels accessible to you. And so clustering is an example of this. Another example of this is principal components analysis. The next category, there's some debate about how it falls and how it should be like termed, but it's self-supervised. And so that's when you learn patterns from the data using the data itself as a label. And an example of this, and we're actually going to implement this today. And so this image that I'm showing is something that you guys are going to do today. The idea is if you have some type of signal, in this case it's a time series signal, and here the blue is the original data and the orange is the reconstruction, we don't necessarily have a label for this time series, but we still want to be able to learn about the data. So what our model will actually do is our model is going to take the original data and basically use the data it has as like the signal to learn on. So how can the model reconstruct the time series signal? Doesn't have the label, doesn't have like another time series signal, it just wants to learn this. Laura.
Self-supervised, basically supervised, but instead of the bimodal classification, you have continuous data set with different.
So self-supervised, I would actually put it closer to unsupervised. It's just what are you using to like learn from itself. So you never have a label. It's a little confusing. So you can, by label, I mean you don't have like a class, like, oh, the apple picture belongs to the class apple. In the self-supervised case, you don't have like a class that the data belongs to, but you're using the signal that you have to learn from itself. And so it doesn't necessarily have to be a time series signal. It can also be like an imaging signal. And you don't necessarily have to learn from like the entirety of the signal. It could even be like, oh, I have the first 20 time steps and I want to learn from I want to predict the next 20 time steps. So you can count that as self-supervised. Or I have 20 time steps and I want to like reconstruct those same 20 time steps. So these divisions are not super clean, and you're going to learn more as we get into the notebook today, different ways you can implement it. But I would think of self-supervised learning as being closer to unsupervised learning as compared to supervised learning. Yeah. Waylon.
Is regression fall into any of these categories?
Yeah, so if you have a label, I would say it's supervised learning. Yeah.
And I'm just trying to relate, for example, what we did with the regression, can we say that is a classification task?
So with the regression that you guys were doing before, remind me, like, why don't you, for everyone, just like say the problem that you guys were doing?
It was using a time series of different neurons to predict attacking or not, for example.
Right. So in that case, because you have the labels and because you're trying to see whether or not you can regress out that label, I would put it in the supervised case. Yeah.
I see. Because I just want to make it clear, because you have these 3 categories of classification, clustering, and regression.
Oh, I see. Yeah, so those are just, I can go back. Okay. Yeah, so these would be examples of tasks, not examples of learning paradigms. So you can have many types of tasks that fall into a learning paradigm. So there's a little bit of like a hierarchy here. Yeah.
Got it, thank you.
Yeah. Let me go forward.
Sabera,
Yes?
why would you consider PCA as unsupervised compared to self-supervised? Because we're actually using the amount of variance in the data
Yeah.
to sort it, so it's actually something from the data.
Yeah.
Right? So,
Yeah, that's a very good question. And I would say that the definitions are blurry and fuzzy. So I think you can argue it either way. It's a little bit difficult. So one of the ways you can think about it is unsupervised is, oh, I want to learn patterns from the data using the whole data set. With self-supervised, you can almost think of it, I want to learn patterns about the data that I'm dealing with for like the data example that I'm looking at. So that's how I think about it. People have different viewpoints, and it is like a fuzzy boundary, and I think you can argue it either way. And I don't even think that there's a clear like definition in the field for what, for like these edge cases, what counts as unsupervised, what counts as self-supervised. Yeah. Okay, good questions. Keep them coming. All right. So all of these learning paradigms that we just went through utilize features in the data to accomplish their task. And so this idea of like features is a common theme in machine learning, and that is that the representation of your data matters. And so sometimes we can actually handcraft our data features, and I'm going to give you guys an example. And so in this case, in the original data set, you have 2 classes. There's this outer class and then this inner class. I don't know if you guys can see the colors. One is kind of orange, one is blue, and there's like a tangled representation. And this is in a coordinate system. Now what we can do is, because we're looking at the data, we see that it's not linearly separable in this first representation. We can actually transform it to polar coordinates, and when you do that transformation, you can see that it becomes linearly separable. So this would be an example where we see what our data looks like. We think that there's a very like clean solution to make it linearly separable. So we're going to go ahead and do some feature engineering or some data set engineering to make it an easier learning problem to solve. And so here the task would be classification, because we want to like classify a boundary between the blue and the orange, and how can we make that as easy as possible. So that would be a case where we actually want to handcraft these features and like get a better representation because we've done this feature engineering. Other times we let our algorithms learn the important features in our data, and that is an example of representation learning, which I think kind of comes back to the question that you were asking earlier. Okay. Does this distinction of, modifying your data to make it easier to learn versus having the model learn the representation itself and not putting in information make sense to you guys? Yeah? Okay, good. All right, so but what exactly is a representation? And this is a question that I'm asking.
basically, you can use classification to do representation.
But classification isn't the representation itself, right?
No, you can use it.
Yes. So what do you mean by that? Expand. What do you mean by using classification to do a representation?
I have data, and it's like super fuzzy, and I don't know how to represent it properly, so I can separate between the 2, and then I use the classification algorithm.
Yeah, so but then what you're doing is you're actually looking at the task, right? So what I'm asking is the model that you're doing to get that classification task creates some representation. Maybe it's lower dimensional, maybe it's not. But what is that representation? Like, how would you define it?
I have the answer here, so
Okay, well.
it's
All right, well, if you're looking at the slides, with the question pieces, maybe don't look ahead. All right, I guess on that, I'll say an encoding of your input data. So when I actually got asked this question for the first time, what I answered was a lower dimensional representation of your data. But that's not necessarily true. You could have a higher dimensional representation of your data. It doesn't have to be lower dimensional. All it has to be is an encoding of your input data. The statement makes no justification for the task you're trying to do with it yet, or with how useful it actually is. So think about a representation as just an encoding. All right, the next question for people that are not looking ahead on the slides. What makes a representation good? What do you think are qualities that make this embedding useful? Jayu.
Usually lower dimensional representation is thought to be better because we can understand it with our limited brain power. If it's like 2D or 3D, we can understand it better, so that probably makes a good representation.
Okay, so you mentioned two things that I think are important for people to think about. And so one of them is lower dimensional and the other is interpretability. And so what I want to ask you is, okay, let's say our task, it's a classification task. And let's say you can get an interpretable embedding, but you get, I don't know, classification of like 80%. Or you have a non-interpretable embedding, but it gets you a classification score of like 99%. Do you really think, or do you think that the interpretable representation is better?
I personally think it depends on what you're trying to achieve with your publication, for example. Maybe neuroscientists us trying to understand how stimuli trigger responses, how behaviors are, the underlying dimensions of behaviors. We would prefer like 80% account for 80%, but like interpretable results. But maybe a machine learning expert would prefer to have an algorithm that solves the problem 100%. So it really depends on what your goal is.
Okay, that was good. I like the last statement that you made. So what Jayu said is that it really depends what your goal is. And I think that she's absolutely right. Sometimes people might, like neuroscientists, we might care more about interpretability versus somebody that's more of like a software engineer cares about performance. They don't care if it's interpretable, they just want it to work. And she brings up a really good point that it really depends on your downstream task. So if what you desire out of your model is something that's going to be interpretable, then that is what you might prioritize over having good accuracy. But if you just care about how it classifies, I don't know, dogs versus cats, then you just care about how high can I get that accuracy. So a representation is only as good as what you want to do with it. And that's an important concept to keep in mind. And so this also goes back to one of the other things that Jayu said. So first thing, ideally your representation is useful for solving many tasks. It's not always the case, and sometimes it's not important, but it's an important thing to try to get out of your models. Another and second point is that if your representation is interpretable, that is great. Although this can be very challenging. And you guys are going to dig into this a little bit more today in the working session to see if you can get, like, what types of representations can you get with neural data. I'm going to ask you whether or not you think it's interpretable. You're going to try to make it more interpretable, and we'll see how well it goes. But does this make sense? The idea that a representation is an encoding of your input data, and the thing that makes it good is just how well you can do the downstream task. Laura.
Because I would think that it would be better to define exactly what you want and build something that does only that, but that we will.
Yeah. Well, so wouldn't it be better? So let's say you have two tasks and you have one representation. So, okay, embedding A will give you performance on task 1 of like 90%. Embedding B does performance on task C at like, I don't know, 80%. But then there's a single embedding that does the performance like as well on both, like better than both of them, the individual embeddings. Like I think we would all prefer an embedding that captures everything we can about the data. So you're right that it's not always possible. And if the downstream task is to be able to like have high performance, then that's the way we should go. But if we can strive to make our embeddings be like descriptive of the data in such a way they can do many things, then people generally agree that that would be a better representation. Does that make sense?
Yeah, I would reword it from solving many tasks to being as representative of my data as possible.
Yeah. Yeah, makes sense.
I had a question, but yeah, I realize you kind of answered it. It's like, I think here when you're referring to encoding, or maybe I'm not sure that you don't want to kind of distort the data such that it fits your goal and your model, and the data should represent the actual reality of the data of the situation, not make it such that you solve your goal and that's what I wanted to do. But you mentioned that if it solves as many tasks as possible, then it encompasses, yeah. So.
Yeah. Yeah, and I mean, I think, so this goes back to, I think many of us are scientists in the room, the desire of having like that interpretability. Like it shouldn't just be for like the downstream task, but we should also kind of understand like how is it encapsulating the variance in our data if that's what we want it to encapsulate. So.
So if you have a low dimensional representation of your data, how can it be not interpretable? I mean, yeah, it might be very difficult to interpret, but eventually there is some interpretation, right?
Does someone, okay, I'm sure there are many experimentalists in the audience that have gotten low dimensional representations of their data, and I want one of you guys to answer Amit's question first, because I'm very certain that one of you has taken high dimensional data, compressed it, and like hasn't gotten anything from it.
I mean, the fact that you didn't get doesn't mean it's not there, you just couldn't find it, right?
Well, but wasn't your question like about the interpretability of it? Like, just because it's a low dimensional representation doesn't mean that it's useful.
Useful is something else than interpretable, right? So you can interpret it, but the interpretation is not useful.
Sure. So, okay, so in some of the work that I've done, and we can, so we're not going to do this data set today because it was actually too hard to actually train in the amount of time allotted. But one of the things that we look at is human ECOG data, and so you've got like many electrodes across time. And if you actually try to like compress that into a lower dimensional space, like even if you count like 1,000 like features as a lower dimensional space, because this data is in like the 10,000 to 100,000 like feature space, it's neither interpretable nor useful, nor does it give you something interesting. And so there are cases where the data that you're working with, it's very complicated to do it in like a linear way, which I don't know if that's what you were alluding to. You could do it in like non-linear ways. But there certainly are examples where it's not necessarily useful or interpretable. Yeah.
I mean, I guess maybe it's just not enough.
Not enough in terms of like the lower dimensional features, or yeah, I mean, so that's true. And sometimes it's not necessarily the number of features. Sometimes it's like how you actually do that transformation. And so there's like a trade-off between how many features do I have versus how am I like finding these features. And we'll explore that a little bit today in the notebooks as well. Okay. All right. Okay, so now that we know a little bit more about the types of learning in data and data representations, let's jump into some of the components of learning. All right, so we're going to do this example with supervised learning because it's the most straightforward. So first, what you have is data. And so here we have an X and a Y and an N and an I. And so I don't know how many of you are familiar with this notation, but we're going to follow it. So X is X and Y are our data examples. So X is your data, Y is your label. There are capital N examples, and I just iterates through the number of training examples that you have. All right. Data can then be fed into a model, and this model is f of theta, and you take an x, which is your data instance, and then it outproduces y hat, where y hat is like the reconstruction of y. So maybe that's like, oh, I want to guess whether or not this is an apple or an orange, and y hat, so my input data is an image with the label apple, and the model is going to take in that image data of an apple, and then it's going to outproduce either apple or orange. And so then what we want to do is we want to feed this into a loss function where loss is the fancy L, and we want to compare y, which is the true label, and y hat, which is like what our model outputs. And then once we have this comparison between like what y is and what y hat is, we want to feed that information back into the model and update the model parameters, which are theta, and this is the process of learning. So you have data, you feed it into some model that you define, you calculate how well the model is doing with a loss function, and then you use this loss to update the model parameters. All right, does this make sense to everyone? Yes? Okay, good. All right, so let's talk a little bit more about models. And here I want to give some intuition behind, I'm sure we've all heard of like very, very fancy, complicated models. You might have seen like DALL-E 2 come out. And I want to just explain a little bit about how data is important, because a lot of us here have domain expertise and we want to be able to build models that will work with neuroscience data. And so it's important to consider your data before thinking about the type of models that you want to design. And so models are very successful when they exploit domain knowledge in the data. And so an example would be convolutional neural networks, which does images. And so for those of you, and this is a GIF and it should play, for those of you that, there we go. So for those of you that don't know what a convolution is, basically if you have an image, which is this green underlying, I guess, array of ones and zeros, you can take a filter, which is the orange, and that's what it's trying to represent, and you can slide it over your data. And then what you can actually do is you create this like convolved feature, which takes in, you can see that the orange is like the top left piece of the filter is multiplying by 1, the next one is by 0, the next one is by 1, and so on and so forth. And it tries to like compress the data. It's doing this convolution in this image space. And so what this will actually do is you can create models that you have some input image. This filter can also be called a kernel, and you'll slide this kernel over your image, and you're going to try to create like compressed basically representations of this image. And the underlying domain knowledge insight is that with an image, pixels that are beside one another are very like similar often in like pixel value in either like their color or the brightness or anything like that. And so when you take like your filter or your kernel and you slide it over, you're actually kind of doing this scan. And some people have even said that it's almost like how we as humans like do saccading. So obviously that's not proven, but that just gives you an intuition for how we can use the fact that nearby pixels are similar, and we can build this domain knowledge into our model and actually make it work very well. Another example that we'll go into a little bit less is the idea of recurrent neural networks. And so these work very well with sequences, and they've been trained a lot in like the natural language processing community. And so here, the idea is that if you have a sentence, word 1 is often connected to word 2, is often connected to word 3, and there's local information. And so you can use the fact that sequences, nearby elements are very similar to one another, and you can pass that into your model, and that will assist with the learning process. And so we're not going to go into these models, but all of them, they have this sentence, I access ... account, and what these models will do is they take in like a word and they will actually process that word, and then when they move on to the next one, they'll process that one, and there will be like this sharing of information as the sentence is being processed. And so the idea is that words that are close to each other probably share more information than words that are sentences or paragraphs away. And so what I wanted to brainstorm with you guys right now is what are some examples of neuroscience domain knowledge that we could bake into our models? Yeah. Okay, so how would you go about like baking that into a model? What do you guys think? How would you go about implementing neurons that fire together, wire together?
Strengthening both are active together to make them next time more active. Okay.
Yeah, so basically like perhaps in like your network when you're trying to learn the weights, if they're like upweighted, or like if the data is upweighted at the same time, upweight the weights in like the network at the same time. Yeah, or vice versa. Okay, how about other ideas? I know a lot of you guys probably transform your data into frequency space. Do you have any ideas about how one might bake that intuition into a model? No? Okay, so what some people will do is they'll actually, there's a recent paper on human ECOG data where what they do is they'll take their data and there's actually a layer in the network that will transform it into the frequency space, and they'll try to learn features both on the time series data that they have and the frequency data. Because I'm sure a lot of you have seen your time series data. You do have characteristic events in, like, you know, if you're in speech in like gamma or in like alpha or beta, et cetera. So definitely when you're thinking about even your own data, especially as we approach Bring Your Own Data Day, how would you want to like use features for the data that you have? So do you care about certain frequencies that might be harder to understand in the time series space? Do you have like a model that you want to implement where neurons that fire together wire together? So think about these like underlying properties of the data and think about how could you transform this into like a set of rules that you could actually implement in math and implement in your model itself. Yeah. Does this make sense to people? Yeah. Probably an abstract. We will get into like the details of how one might do this a little bit later today. But at least in abstract, it seems like it makes sense. Okay, good. All right. So here, what we're going to do now is we're going to go into a little bit more on losses, and we're going to do an example. Okay, so we're going to explore losses in the context of parametric models. And these are models where all the information is represented within its parameters. And so the question really is, for fixed data, what are the best parameters to explain the data? So that's the question that we're going to try to answer. And so we're going to look at this with a sinusoidal model. It's pretty straightforward, so I hope everyone will kind of see what's going on. So here we have some data. So the data are these blue dots, and we actually generated them by creating this red line and then sampling from the red line and adding some noise. So the blue data is the thing that we are trying to learn, and we can have a few models that we actually use to try to learn that data. And some of these models are better, some of these models are worse. And so the data, as we're doing learning, the data is staying fixed, and learning with this model means picking the 3 parameter values. So the function is at the top where it's f of x, theta 1, sine, and then within the parentheses, theta 2 times x plus theta 3. And then at the bottom, we can look at the exact theta values. They don't matter too much. But basically what we're trying to do is we have this data. We want to learn what is theta 1, theta 2, and theta 3. And how are we actually going to go about learning what this theta 1, theta 2, and theta 3 are? And so how do we pick them? Does anyone have an idea for how we would go about picking these theta values? All right, Brady, I'm looking at you.
You could randomly generate them to start.
You could.
And then check your loss.
You could. Okay, so loss. So that's a good point. You definitely could. Another thing we could do, and what's probably important, is we have to define our loss function, right? Like, how are we actually going to judge whether or not the lines that we generate encapsulate the data that is like underlying? And so do you guys have any ideas for what loss function that we could use? And you have encountered a few loss functions already throughout the past few days. So even if you're like, I don't know what a loss function is, you do know. Okay, shout out loss functions. Good, all right. That is a loss function that you have covered, and that is the loss function, or sorry, how you pick them is gradient descent. You have to do gradient descent on a loss function. We will look at a loss function. And yes, indeed, the loss function that we're going to use is mean squared error. And so I think you guys have all used mean squared error by now. Hopefully you know how it works, but just to make sure that we're all on the same page, you have this model, f theta, that takes in an x, and that's like a prediction. You want to compare whether or not your ground truth, like how well does your ground truth match the prediction that you create. And then what you're going to do is you're going to take the difference, you're going to square them, and then you're going to sum across all of the examples that you have. So this is what you've been doing when you've been calling like MSE loss for whatever models you've been working on so far. So this is what we're doing. And if we calculate the mean squared error for the red line, the blue line, and the green line compared to our initial data, we're going to get something that looks like this. So you've got L1, L2, and L3. So what do these loss functions tell you? We'll start with which one is the worst? Okay. Yeah, how about we just do raise hands? Okay, which one is the worst? Do you think it's L1, L2? You guys are very confident. Raise your hands high. L2 or L3? Okay. And then, sorry, what?
That's kind of weird because I will assume that, you know, the higher number is the worst because clearly L1 is great and it is the lowest. But when I look at them on the board, like, I don't know, L2 doesn't seem like the worst to me. I would prefer that than L3. But...
Okay, so I'll just repeat it for Sam and Mingyu. So basically, when we're looking at the loss functions, it's and you guys are right. L1 is the best. It has the lowest value. And here we're doing minimization, so we want to have low loss values. L1 is low, and that is the best. And the higher ones are worse. So L2 is the highest, indicating that it would be the worst. And L3 is, you know, somewhere in the middle. It's closer to L2 than L1, but it's also, you know, not great. And indeed, according to this loss function, L2 is the worst. And the idea that I want to demonstrate here is we've all kind of seen like, okay, if I had to pick between the green one or the blue one, I would rather take the blue one. And I think everyone kind of agrees on that. But the green one actually gives you a better value for this loss function. And so something that you really have to consider is that the loss function that you're optimizing is very important. And maybe the loss function doesn't actually encapsulate all the data that you want it to. And you kind of saw this on the first day where I think Adi had you add in like regularization terms. And you basically changed your loss function because you weren't getting what you wanted to with the data. And so, yeah, we prefer the blue plot. And if we prefer the blue plot to the green plot, then what we'll need to do is we're going to need to change our loss function to actually encapsulate the fact that that is the signal that we prefer, not the green one. And so always come back to the idea that even though something looks better to you, the only way you're going to know what is or is not good is by the loss function that you're using. Okay, does that make sense to everyone? Okay, good. All right, so we were talking about this earlier today about calculus and derivatives and gradients. And so the way that you actually figure out, you know, whether or not you have good values is by taking gradient descent. And so when we look at the loss gradient descent values, you've got, these are the gradients for L1, L2, and L3. And you can definitely see, we're going to go into this a little bit more, but you're going to see that the red values are smaller, the blue values are bigger, and the green values are also quite big. And so inside each of these gradient vectors, element I is how much the loss changes when you change that theta I. And so we're going to walk through some like high-level takeaways, and then we'll return. Actually, I think I have it on the next slides as well. We're going to walk through some high-level takeaways so that you guys understand what you're looking at when you're looking at what a gradient is. And so takeaway one is that the red model performed best, and the gradient values for the red model are very small because it's good. So in this case, we're doing a minimization problem. We want the, like when we wiggle our theta value in our function that's up here, this theta1 sine theta2 times x plus theta3. When we wiggle those theta values, our gradient values doesn't change very much. And that's because the loss doesn't change very much. And so you've kind of approached this solution that works well. When you change theta, it doesn't change your loss values too much. It indicates that you're doing a good job. The next takeaway is that the blue and green models are bad. So the loss changes a lot when we perturb the parameter values. So for the blue function, if you change your theta value, you're gonna get a very different loss value. And that's because they're not so good. But when we look at the takeaway 3, if you actually look at the green loss gradient, the gradient vector for L3, the third one, in the bottom, theta 3, the gradient information is very local. And the third element of this green gradient is small. So it's like 0.004, I think. And so that doesn't mean that the parameter values are good. It just means that the current parameter values changing theta 3 slightly, it's not really going to change the loss that much. Okay, I'm going to, actually we'll pause here. I know I just gave you guys a lot. Gregorios is smiling at me. Do you have any questions?
Yeah, I have lots of questions, but
Okay.
not enough.
How do you compute the loss value values?
So the black equation at the top, so that is the equation that we're using to compute it. And the general form of how you compute a gradient.
The loss gradient function is just a gradient?
So yeah, so you can think of basically the gradient function as taking derivatives with respect to the different parameter values. So we're taking, the first one would be taking the gradient with respect to theta 1, then with respect to theta 2, then with respect to theta 3. And so you will never, if you want to, you can, but you will never have to take a gradient value when you're doing anything in machine learning. Like the field is progressed far enough such that there's just code that will do it for you. You don't even have to think about it. But it's important to understand that what you're doing is you're taking a derivative with respect to a parameter value, and you're seeing when I wiggle that value, how much does like basically my trajectory on this loss curve change. So you will, if this scares you, that's fine. You will never have to do this. But understand that there's this like loss landscape, and basically you're either trying to find a minima on that loss landscape or you're trying to find a maxima on that loss landscape. And that's the important conceptual idea to take away.
Yeah, no, now it makes sense because now I understand why you don't change a lot.
Yeah. Okay, good. I'm glad. Any other questions? Gregorios, if you have a question, you should. Okay, we'll come back to it. Oh, I think we might have a, don't know if we have a question on Zoom. I can't see. Okay. All right. So another thing that I want to really hit home here is that the model family we choose is important, and no linear model is going to fit the data well in this regression problem. So understand that, and this kind of goes back to the idea of our underlying data. There are interesting, like domain-specific things about that data, whether or not it be images or neural data or sequences, where certain model classes will just not be able to work on certain data types. So you always have to think about, what am I asking my model to do, and can it even do that with the data that I'm providing to it? So always think about, like, does the data work with this model, and does that work with the loss function? So data, model, loss. You should always think about how those three things are going to interact with one another. And then moreover, you have to choose like a sufficiently expressive, in this case, parametric family. But in all modeling cases, you have to choose a model that's going to be sufficiently expressive for the question and the task that you're trying to get it to answer. Okay. And I think I have one more slide just on gradient descent to solidify the idea. So gradient descent is the easiest way to optimize our learning objective. You will never have to take a gradient if you don't want to, but it is the easiest way to go about understanding it as well as actually computing it. And it's a method that changes the weights of your model so you can approach, in this case, a local minima. In other cases, it could be a local maxima. So in a succinct way, that is what we're actually doing when we are looking at this problem. And we're trying to find which of these solutions works best for it. Okay. Does this all make sense to everyone? Yes?
All to everyone? It's a high five.
Okay.
I guess the question.
Do you want to ask a question? If you have a question, you should ask it.
No worries.
Okay. Brady.
Could you explain again exactly what we're looking at in those vectors? Like what those numbers mean?
The numbers on the far right,
Yeah.
in the vectors.
Yeah.
Yes.
So I get that that's how much, that's, well,
Yeah, maybe let me go back here. Okay, yes. So each, okay, so honestly, I wish I could have just blocked them out and only focus on it. So okay, let's just focus on the red one first. Actually, let's go back. Okay, so the top equation, this black equation at the top, this is what we call a gradient. And basically what you're doing is you have your mean squared error function. And what you're doing is you're taking the derivative of that function. So let me go back. Okay, yeah, so this is the mean squared error function. What you're doing is you're taking the derivative of that function with respect to each element. And so here, in the top case, we're taking it with respect to theta 1, and then with respect to theta 2, and then with respect to theta 3. And so that's like the vector itself. And so when we're looking at the red or the blue or the green, that's just what happens when you plug in the values for like the theta that you're looking at. What are the values that you're actually getting? Of course, summed over all of the training examples n. Okay, so within these vectors, each element of this gradient vector is how much the loss changes when you wiggle that theta I. Okay, and to recap, for the red piece, when I change theta 1, like the value is, I don't know, negative 0.0033. And that doesn't, so basically if I change theta 1 just a little bit, I'm not actually getting a huge improvement in the loss with respect to theta 1. If I then look at theta 2 and I wiggle that, I get also a very small number, and my loss doesn't improve that much with respect to theta 2. And then same thing with theta 3. And so what this is telling you is that in this loss landscape, when I change theta 1, I'm not getting too much improvement. When I change theta 2, I'm not getting too much improvement. And when I change theta 3, I'm not getting too much improvement on the performance of my model. And if I'm not getting too much performance improvement, then it means that perhaps I've reached like a minima and my performance is actually good. Versus when you look at the blue or the green curves and their respective gradient vectors, when you wiggle, so let's just look at the blue one. So with the first element, which is the gradient with respect to theta 1, I get 0.33. And so when I wiggle theta 1, I do actually get a change with like the loss value. And so that means probably I haven't like learned a good theta 1 in this model. And if I change it, I can actually get to a better solution. Does this make sense? Okay.
But the output here, for example, for like the green one,
yes.
Like the very small value of like the theta 3 does not really mean that it's a good theta 3.
Right. So yes. So it means that it does. So the gradient information, when you take it with respect to one of the parameter values, doesn't necessarily mean that it's good over all of the parameter values. And that's the problem that like we're seeing here. So you have to, and this is basically getting at the point that you have to look at how you're performing over all of your parameter values, not just one parameter value. Because if I just looked at the last one for, you know, the third example, the green example, I'd be like, oh yeah, like I'm done, I'm performing super well. But then when you look at how it performs with respect to theta 1 or theta 2, you're not actually performing well. So you have to, and which is why oftentimes what you're going to see in like the models that we do today is you report the loss value as like one value. You don't report it for like each parameter value. And so you want to get some aggregation over how the model is doing in totality for all parameters, not how the model is doing just for each independent parameter. But during the learning process, it's important to know how we're performing with respect to each parameter, because then we can like wiggle the parameter that's not doing well. Does that make sense? Okay. Good. You look like you have a question. No? Yeah, no, Nayan, you look like you had a question. Okay.
I think it's for the latest thing you just said. If I were to, on the green thing, okay, it's like I have a very small number for theta 3, right? So I'll keep that fixed, and I'll start moving other things. But I know that the ideal theta 3 that I will get from the red is like 0.76 versus the theta 3 that I get for the green is minus 0.5.
Right.
So even if I fix theta 3 on the green, I start moving the other ones. Will that somehow?
Yeah, so the thing, okay, so the thing with this, these are sinusoids, and so because it repeats like 0.7, it doesn't have to be 0.76, right? It just has to be a repetition of 0.76. So, but yes, you're right. So the idea that if I wiggle one of the parameters and, you know, for some reason, then the rest of them don't work out, then you have to keep looking at all of your parameters and making sure that you get performance over all of them. Yes. Okay. All right. Everyone good? No more questions? Okay.
But just to make sure.
Yes.
So in this case, so comparing the gradient values from different models is like not useful. Each like
the individual gradient values.
no, I yeah, for example, for those models that like work perfectly well, like compared to like the blue and green ones, does not really like provide some information that which one is bad because they're both not so good.
Yeah. Okay. So the gradient values tell you, which one is worse and how you want to wiggle. So like, which parameter should I change next? For theta, or for the second model, I'd probably pick like the middle one because it has like a large value. In practice, though, this is not how you train models. You will never look at the individual gradient values. This is more just for instruction. So when it comes, I think you're asking a question about like in practice, what do you do? And in practice, you're not going to compare like the individual parameter values. In practice, what will happen is you're going to have an aggregated loss value for like, how does my model perform for like all of the parameters, not just an. And then what you're going to do is you're going to optimize your model for that aggregated loss score. So in principle, like, which is what we're showing here just so that you guys have some intuition behind how we change one parameter value and it changes the loss. This is how you might think about updating a model. In practice, you will not look at individual gradients on individual parameters and wiggle only one at a time. Yeah. Does that make sense? Does that answer the question? Okay. All right. You guys good? All right, I think we're about out of time, so let me just see if they have questions on Zoom. Mengyu or Sam, do you guys have questions on Zoom?
No, we're good. I'm good.
I just want to clarify since I couldn't hear the question people asked. Okay. So the gradient is, the small gradient is a necessary but not sufficient condition for a good model.
What do you mean the small gradient?
The gradient is small, the gradient numbers.
Oh, you're saying like, can you see my cursor? This value here, you're saying having, I see. Yes, so yes, ideally you want, in the case where we're doing a minimization problem, what you want is you want to have like a small loss value. And ideally you want to have, when you wiggle a parameter, you want the gradient value to not change too much because it indicates that you've approached some minima. Of course, it could be like a local minima and not a global minima, and so there's a little bit of complication there, but in general, yes.
I see. So, but the if we change the parameter and the loss doesn't change much, it doesn't have to be a good model because it's probably the loss itself. No matter how what the parameter you set, like the loss is very high. So in that case, you also will see a small gradient, but that doesn't mean that's a good model.
Yes. So I mean, at the end of the day, you want to make sure that the loss function itself is performing well. So I think you're alluding to like the third case, which is the green case, where you do have a small gradient value, but like you're not actually performing well. Yeah. So I think you said it right about the necessary and sufficiency.
Okay, got it. Thank you.
Awesome.
So just based on these, it still doesn't seem like the blue model, at least, is indicated to be better than the green model, even though that's what we see at a glance, even though.
Yeah, and so that's the purpose. So the idea is that you might not have heard this because I think Gregorios was the one that was mentioning this, but the blue model has the worst. Let me go back. The blue model has there we go. The blue model has the worst like loss value. And so even though when we visually inspect it, we think we would prefer the blue value because of the loss function that we chose, it's not the one that we would pick. And so this is just like a cautionary tale to make sure that the loss function that you pick is in line with the behavior that you want to see of like a good model.
I see. Thank you.
Yeah. Okay. All right, we are about at time. We're actually exactly at time. So we will pause here and let you guys go to the philosophy section, which Lior and Isong will be leading for you. So there we go.